Hello, algebra students. We have already worked on building some quadratic functions, writing the equations. We talked about dropping something from a height and looking at either how far it has fallen or how close it is to the ground. And today we're going to look at a different kind of motion. Instead of just dropping something, we're going to have something being launched or thrown up into the air. And you guys know, like you've seen this, when you throw something into the air, it doesn't just keep on going forever and ever and ever. Realistically, there's some gravity that's going to start to pull this down. So if we have a cannon, and this cannon is set 10 feet off the ground, and it launches a cannonball straight up into the air, not shooting it like at something else or trying to have some kind of an angle. It's going straight up into the air. The velocity, the speed, is 406 feet per second. So we're going to do this first table and pretend like there's no gravity. We are not worried about gravity at all. So we are going to say that at 0 seconds, so before it even leaves the cannon, that cannonball is 10 feet off the ground. After 1 second, it's going to travel 406 feet. Every single second, it's going to travel 406 feet. So after 1 second, it travels 406 feet, but it was already 10 feet off the ground. So that's going to put it at 416. And then it'll travel another 406 feet. So we could just keep adding 406 on here. That'll get us to 822 feet. Notice I'm not labeling just for space, but you know this is all in feet. And then after 3 seconds, it'll be at 1228. At 4 seconds, it's going to be at 1634. And at 5 seconds, it would be at 2040. Now, realistically, I wouldn't want to have to do this and keep adding 406 every single time. But we know how many times we're adding 406. We're adding 406 for every single second. So the t is going to be the number of seconds that we've had. But remember, the cannonball started at 10 feet, and it's going to increase in height by 406 feet every single second. Okay, so number 2 asks that same thing. It says, what's the equation for this? Well, I just wrote an expression in the table, but the equation would be that the distance that we've got right here in feet would be equal to 10 plus 406 t. T is the number of seconds that it's traveling. Now, realistically, we know that's not just going to keep going forever and ever. It's not just going to keep on going out into outer space, right? Because there is gravity. So we've got this actual table here. This is showing what the real heights are. Let me rewrite what we had here. At 1 second, at 0 seconds, it was 10 feet. We had 416, and we had 758, and 1084, and 1634, and 2040. So you can see there's clearly a difference in these heights. And I want to think about 2 things that you notice about this, right? When I'm looking at this, I'm saying the actual heights are definitely less than the theoretical, like the no gravity heights. The actual heights are definitely going to be less than that. And then the other thing that I'm noticing is that the differences aren't consistent, right? At 1 second, it was at 400 feet realistically, like with gravity. That's a difference of, I'll switch colors here, 16 feet from what it would have been with no gravity. But then the next time that I measure this, it is at, oh, I wrote the wrong number right here. I am so sorry. I wrote the 758 that was already there. This was 822. So that difference, if I subtract that, would be 64 feet. And then I did the same thing here. Not 1084. That's supposed to be 1228. And when I subtract those two, I get a difference of 144. And then I get a difference of 256, then a difference of 400. Now you may notice something special about those numbers. We used those numbers in the last lesson, right? When we were dropping a shape, a rock or whatever, and we were measuring how far it's traveled, those numbers were in that pattern. So the differences are definitely not linear, right? We don't have a constant rate of change here. So it says that we want to plot those two sets of data. I'm going to just go to the one that's actually done and graphed, and I'll show you that in a second. But we're going to be looking at how the two graphs are alike and how they're different, and then we'll have to come up with an equation. So we just talked about that. Here's the graph. The actual heights are the round circle dots, and the triangles are the ones that are ignoring gravity. You can see that those two are getting farther and farther apart because gravity is starting to slow that cannonball down. Now remember, this isn't the path that it's flying. This is just graphing out the heights that it has. So they are both definitely increasing. That's how they're alike, right? The triangles, that is a straight line. It's linear. We can see that that is just totally ignoring gravity, but the equation that we had for that was distance equals 10 plus 416. It looks just like slope-intercept form. So we know that that one's going to be linear. But the actual heights are definitely not linear, right? They both start at the same place. And I know it looks like on here that they're both starting at the origin, but remember that first point was at 0, 10. When we're counting by 500s on the y-axis, 0, 10 is going to be practically at the origin anyway. They both start at the same height because we're saying the cannonball, the cannon, started at 10 feet. And again, as we're watching what's happening here with these actual heights, as the differences are increasing, it's really that the actual heights are slowing down. They're not growing as quickly. Now, well, and I have the equation already kind of showing here, but I want to show you where all of these parts are coming from. This part we already had, right? That's the cannonball. It started at 10 feet. That's the initial amount or the starting amount. And the 406T was how much it was increasing in height every single second. That would be like the, oh, what's the word I'm looking for here? The velocity. That's the word. Right? It was 406 feet per second. That minus 16t squared, we used that in the last lesson. That's the effect of gravity. That's what's slowing it down. That minus 16t squared, that's gravity. Okay. Now, let's see here. That's, yeah, I guess that is the right one. Sorry, I thought I skipped a slide. So this is a different cannonball now. We've got this new function. It's right here. Function is just an equation, right? And it says how far a cannonball, what the height is of a cannonball. T is the number of seconds after it's been fired. So for number 1, it's asking, what do those parts mean? Remember the 50, just like the 10 in the last problem, this is the initial height. That's where it started, right? That's like the y-intercept. That's where we begin. The 312, if you look back at that last one that we just did, that's similar to the 406 that we had from the first cannon. This is the velocity per second. This is saying, I guess I shouldn't say velocity per second, the number of feet per second. That is the velocity. This is saying that without gravity, it would be rising at 312 feet every single second. And the minus 16t squared, that's the gravity. Okay. Now, again, to save a little bit of time, I'm not going to say that we're going to grab a graphing calculator because I have the graph all done on the next slide. But this is if you would want to take a graphing calculator or a graphing program on your computer and type that in. We want to see what that's going to look like, and then we have some questions about this. So let's take a look at that graph. Oh, we already just did this. We know what each of those parts are. The graph looks like this. Now, in the last graph that we had with the no gravity, the ignoring gravity points, and then the ones that actually had gravity, we could see that the ones with gravity were actually curving. This is what it's really going to do, though. This is what it would look like. And again, this is not necessarily the path that it's following. This is how high it gets off the ground and coming back down to the ground, because eventually that cannonball is going to fall back down to the ground, right? So we'll talk about what this means right here, because that has to do with the domain. This is just making sure that I'm looking at the part of the graph that is just the actual height that we need. We don't need this to go up to, let's say, 10,000 feet. We only need it to go up to about 2,000 feet. So we've got this graph. It says, describe the shape of the graph and what does it tell us about the movement of the cannonball? This graph is, obviously it's a curve, right? It's showing the distance from the ground and it's increasing at first. And then it actually, when it gets up to the peak, that's where it's kind of slowing down and gravity starts to be more powerful than the force that it has. And it starts to bring it back down to the ground. So that's when it's decreasing. So we're increasing here. We're going to reach this peak right there. We're going to talk about what that's called. And then it starts to come on back down. And again, this isn't necessarily the path that it's following. I'm just looking at the height that it gets to for each of these. And I know that the change is not consistent. For instance, on the way up, until it gets to its highest point, it doesn't go the same way exactly all the time, but it does match up with the descent part of this. When it's coming back down, it looks the same on that side. We've got some symmetry there. For B, it says, estimate the maximum height that the ball reaches and when does this happen? So looking at this graph, it's not a perfect graph to be able to see exactly what it is with the having extra lines in there to see those grids. But I would say that this is getting probably a little bit over 1,500 feet. Probably between 1,500 and 1,600, right? Right there is 1,500, and it's just barely over that. So probably the height is going to be between 1,500 and 1,600 feet. That's the maximum. I want to know when the ball hits the ground. Now remember, when the ball hits the ground, that's when the height, the distance from the ground is 0. That's going to be right here. Right? Not quite at 20 seconds. So it's going to be less than 20 seconds until it hits the ground. Number 4 is the domain question that I said we would come to. The domain is what the x's should be, what the time should be. So this cannonball is hitting the ground before 20 seconds. After 20 seconds, it's already on the ground. None of those numbers make any sense after that. And first of all, we can't have a negative time, but there's nothing on the graph before 0. So an appropriate domain, numbers that would make sense for this, would be between 0 and 20, right? Because it hits the ground just before 20. Okay, so if the cannonball were fired at 800 feet per second, I want to know if it would reach a mile in height. So let's take a look at that. So if we had This is now a different cannonball because it's got a different velocity. This is, let's see here. On my last one, we did start at 50. Okay, so we're going to use the same equation, but we're going to change this number right here to be 800. So it's got a different velocity. So I'm going to have that my height would be starting at 50 feet. It's going to increase by 800 feet every second, but we have to take away gravity. Okay? So I want to know if it's going to reach a mile in height. Now I'm going to, because I happen to know what this is going to work out to be, I'm going to use 10 seconds. Let's see what happens at 10 seconds. The last one, remember, it hit the ground at about almost 20 seconds. So 10 seconds would be about halfway through its path. So here, if I would put in 10 seconds, I want to see what the height is going to be. So I'll have 800 times 10 seconds minus 16 times 10 squared. So I'll have 50 plus 8,000 minus 10 squared is 100 times 16 would be 1,600. And if you would add those two together, you get 8,050 minus 1,600 is going to be 6,450 feet. That's the height that it would get at 10 seconds. Now, in case you don't know this, there are 5,280 feet in a mile. And that is clearly more than 5,280. So it's going to definitely be able to get higher than 1 mile if this is a realistic velocity that we've got for the cannon. Okay, now this isn't in your paper, but let's just take a look and try to pull together some of the stuff that we've done. So we want to look at all of these different equations and where they've come from. So we've got 3 expressions here that represent the distance from the ground. The first one, that was like what we did in the last lesson, where we were just dropping an object, right? So that's the distance that an object travels after it's dropped. The difference between the first equation and the second equation is I'm subtracting that 16t squared. So this is telling me that it started at 400 feet and gravity is pulling it, right? Still just dropping it. It's being dropped from a height of 400 feet. The third one, it's very similar to the last 2 problems that we just did. This is saying that we've got an initial height of 50. So we're starting at 50 and it's got an upward velocity of 100, what's it, feet per second? I don't know exactly what this is being measured in. Oh, I guess it is feet here in seconds. But the gravity is going to be pulling it down. So this isn't just being dropped. This is when I've got something that's being launched, thrown into the air or whatever, but we want something that's going up and then it will come back down because of gravity, okay? Zeros of a function, that's where, if I would graph this, it would hit the x-axis, right? So what I'm looking at here, for the 16t squared, the 0 is when the object has traveled 0 feet, right? This is where I'm measuring how far it has traveled. Well, it's traveled 0 feet at 0 seconds. You haven't dropped it yet, right? For the next one, let me move this up a little bit. For the next one, the 400 minus 16t squared, remember that's figuring out when I drop it, when it hits the ground, right? So it started at 400 feet. I want to know when it hits the ground. I want to know when the height is 0. When it hits the x-axis, that's when the height is 0. So that'll tell me how long it takes to get back down to the ground. And this last one, that's where we launch something. We're going to actually have 2 zeros here. We'll have a 0 before it's launched, if it's launching right from the ground. And again, when it gets back to the ground. So we're looking at where a graph is touching the x-axis, not the y-axis. We're used to looking for the y-intercept. This is about the x-axis for the zeros. Now, this is just our summary. It's on the back page of your handout for this. So we've got some different ways of looking at heights of objects. And this one was more about launching something going up and then coming back down. So an object that's thrown upward from a height of 5 feet. And by the way, doesn't it make sense to have an initial height that's not 0? If you're throwing something, you're not laying on the ground probably, right? So this is saying that you were throwing something and it started at 5 feet. This 60 was that velocity of 60 feet for every second. And then that minus 16t squared, that's gravity slowing it down or bringing it back down to the ground, okay? So I just talked through those parts. When we graph this, here's that same thing graphed. It says that the graph intersects the vertical axis at 5. That's our initial height. That's like the y-intercept, right? It's right there at 5. So if this is like someone, let's say, throwing a ball maybe, and it starts at 5 feet tall. And it's thrown up into the air from 5 feet, and it says that it's up to about 60 feet at the highest point, right? A little bit, well, right around 2 seconds, so maybe right about here. It gets to about 60 feet. That's the highest point. It's called the maximum value or that peak. What we do use, the word that we use for that is the vertex. That's the turning point. Okay, so that's where the curve changes. Instead of increasing, that's when it starts to decrease. This graph is what we have for quadratics. The shape of this, it's got a really cool name. It's called a parabola. Some people want to say parabola, but it's really a parabola. That's the name of that U. Now, these, because we're talking about something going up and then coming back down, these all look like upside down U's, but there will be times when we'll have graphs where it'll be a right side up U. But that U kind of a shape is the parabola, where it's increasing and then decreasing, or the other way around. Sometimes it decreases and then increases. So this, it says, and you can just barely see the graph up there, it says that it hits the ground a little bit before 4 seconds. That is on the x-axis, right? That's a 0. So it didn't actually get down to the x-axis over here, right? It started at 5 feet, but right here, that point right there is the 0. That's the time when it gets back down to the ground, when the height is 0. So if we are looking at domain numbers for the inputs, for the time that makes sense, we would be looking at time from 0 to a little less than 4 seconds. Usually we're not going to stop a graph at like 3.8 seconds. But after 3.8 seconds, after it hits the ground, it doesn't make sense to have the time going anymore because it's already down to the ground. It's not doing anything else. Now, this is your cool down that you're going to be doing. And for this, we've got this rocket. So that's where you stomp on a thing and it gets some air in there and it shoots it up into the air. So we've got this equation over here. Remember this h of t, that's really just like saying y, the height. Number 1 says, how does the 5 relate to the graph? I'm not giving answers on these, but think about what that first number meant in all of our other equations. What does the 100t mean? Remember, the t is the time, that's the number of seconds, but the 100 is important in this equation. And then what does the negative or subtracting 16t squared mean in this? What's happening from that? The last question is, when does the rocket hit the ground? Now remember, I'm looking at when is the height back to 0? That's what we need for that one. So that's your cool down that you have to do. Make sure you check Schoology so you can see what else you have to do and let your teacher know if you need any help.